This is DDR2. Okay, I just want to point out right now the speed of clock speed of DDR2 SDRAM is about 260 megahertz. That's also pretty high. Okay, so you can see the speed start from 100 megahertz, it's increasing to 260 megahertz. Okay, of course, the transmission speed is because it's double edge triggered and so on. So the transmission speed is gigahertz. It's in gigabit per second now. Okay, so this is the speed of RAM memory, and then this is the picture to show you all the spectrums of different devices and so on. So you can see that everything is around gigahertz from 1 to 10 gigahertz. Okay, so if you design digital systems at that range, and then of course the system is going to have a lot of it's going to receive a lot of interferences from other devices. Okay, I also like to follow the development of smart cars. Okay, and this picture is from Toyota. Okay, it's about how you can design cars to be safer. You basically add a lot. You add a lot of sensors. Okay, you can add sensors almost everywhere. Of course, when you add sensors, and then those sensors may interfere with each other, so you need to be able to design those circuits to make sure there's no interference. And of course, the more sensors you add, the faster you need to process them, right? So your computer has to be fast enough. Your network has to be fast enough. So the whole car actually is a computer network. Okay. New cars usually have about around 50 microcontrollers on the car, just for one single car. Okay, and like 5 or 6 years ago, I attended a conference, and then one auto company said their average car has about 500,000 lines of C code in a car. Okay, so it's a lot of software as well. Okay, and then I like this development very much. As I follow this development, and then also computer network on the car. Okay, it's very complicated. Okay, and again, it's very interesting too. So I try to, as much as possible, use examples from automotive electronics to introduce software and hardware. I teach CAN bus. It's a control area network. In my embedded system class, I introduce CAN bus to students. Okay, and I also introduce some of control applications from automotive electronics. Okay, so and next topic is how do we study digital signal transmission? Okay, to study digital signal transmission, we use a time domain description, which is called an eye diagram or eye pattern. Okay, so this is the digital signal, right? Okay, it's a 0 and 1. Okay, and what we do is we cut them into 2 bits pieces. Okay, then we overlap them in space. Okay, so cut them into 2 bit pieces, then overlap them in space. Then we can form a so-called an eye. Okay, so and you can see that some of pieces are low or 0, some pieces are high like this, and some pieces are transmission from low to high, some are from high to low. Okay, so when you overlap them together, you form one piece very. So you can look at this to find out how good your signal transmission is. Okay, this is one example. This is a simulation. Okay, and the bit rate is 1 gigabit per second. The rise time is 250 picosecond. Okay, it's a random sequence. It's a communication sequence. Okay, and so this is a time domain signal. Then if you put them together, and you form an eye, or so-called eye diagram. The eye diagram can be specified with some parameters. One is the eye height. This is the height of the eye, the width of the eye, okay, and then and then some of this so-called jitters, okay. That is, some edges come earlier, some edges come later, so that you have a range of this. This is called so-called jitter. So at least you have 3 parameters here: eye width, eye height, and jitter. Okay. So we can use this to specify how good we can transmit digital signals. Okay. And of course, this is physically, if you add, and you can see that the eye diagram can get pretty messy. Okay. And again, when we transmit this signal, because we transmit digital signal, right, at 0 and 1, as long as at the receiving end we can recognize this as 0 and 1, that's good enough. Okay. So we specify a point where we see this is a sampling point. Okay. So when at this sampling point, if 1 is all above here, we can recognize this as 1. The 0 is all below here, we can recognize them as 0, then it's okay. That's good enough, right? Okay. So that's why the eye diagram can help us to see whether we can still recognize logic high and logic low. Okay. And as the signal is transmitted. Okay. So this is another way to specify the eye diagram. There's a sampling point, there's a left edge, right edge, and there's a cross point. Okay, there's 1 unit here of the eye diagram. Okay. All right, this is one example where the eye is still okay. You can see that at this point, logic high signal all here. We can recognize them as logic high. Logic 0 signal is all right here. We can recognize them as logic 0. Okay, and in between we have so-called noise margin, the voltage offset here, and also timing margin. Okay, we can afford to sample at this point anywhere within this margin. Okay, so because when the receiver samples the signal, you cannot guarantee that it will sample at the exact same time. So sometimes you sample at this point, sometimes you sample at this point. But if you sample at this point, of course, you're going to be in trouble, right? If you sample at this point, you're going to be in trouble. So there's a window where you can sample the signal to recognize its logic high or logic low. Okay. This is pretty bad, but it's still okay. It's not that bad. Okay. But the second one, if you look at that second one, it's very bad. It's almost it's not possible to recognize that signal at all. Okay. Digital signal transmission model. Okay. So when we start a digital signal, when we send a digital signal through a transmission channel or transmission path from the transmitter to receiver, to study the quality of signal, we can use so-called the eye diagram. Okay, so the transmitter has a signal which should be very clean, right? So the eye diagram of the signal before it's been transmitted has a very nice eye diagram. You can see that logic high is right here, logic low is right here. The eye is pretty open, so we can recognize logic high and low. But once the signal is being transmitted through this channel, it goes through. It's on the chip here. It goes through this printed circuit board on this back plane, and then go to another printed circuit board. Then there's a cable. It's black cable, and then to another printed circuit board, and then to this chip receiver. Once the receiver received it, that signal becomes distorted. Okay, that's okay, right? The good thing about digital system is because digital system can take this distortion, right? That's why we design digital systems. Okay, so we can afford to have a little bit distortion as long as the signal can still be recognized as logic 1, logic 0. Everything's fine. Okay, but in between, you can see it's actually pretty complicated, right? They have a lot of traces, cables, and then different material properties, and then the connectors and so on. Okay, every one of them may introduce distortion. Okay, so that's why, in principle, it's pretty simple. I want to send this signal from this end to that end. I want to make sure I can still recognize the signal. That is called signal integrity, right? But in practice, there's a lot of factors. Okay, so, and if you zoom them in, you can see that this is the transmitted signal here, and then you can see that this is the printed circuit board. Okay, and then the connectors. There's the connectors here, and there's veer. This is the veer that may affect the signal transmission. Then there's cable. Okay, from here, between here and here, there's a cable that may affect the signal transmission. And there's a driver receiver. Okay, there's a driver here. There's a receiver here. Okay, that may affect a transmission as well. So there's a lot of effects that we need to study. Okay, so it's actually pretty complicated. Okay. Some books, there are actually high-speed digital design books. One of them by Brian Johnson. He's a adjunct professor at UC Berkeley. He wrote 2 or 3 books, and his book, one of his books is called High-Speed Digital Design, Black Magic. Okay, and then another book is Advanced High-Speed Digital Design, Advanced Black Magic. Okay, so he called them black magic because basically it's magic. Okay, but it's not. It should not be magic. It cannot be magic. Engineering designs are not magic. Okay, because engineering designs, we follow rules, we follow principles, and then we know what we're doing. Right? We don't just throw a dice and then make it happen. Okay, so it's not about black magic. It's about systematical design. Okay, so this is a high-speed design flow. Okay, so you specify your system, and you do a system-level design, then you do verification, optimization, simulation. Okay, then you analyze your performance of your system. Okay, and you do a prototype, and you do a design verification, and you do production. Okay, so there's a iteration here where you actually analyze your design, make sure your design will meet specifications. Okay. This example, this is a 10-bit, 10 gigabit per second backplane design. Okay. All right. Let me go to this simple model. Okay. Actually, the model is very simple. Okay. What we want to do is to go from here, that's the driver, it's a CMOS driver, and to send the signal through this signal trace to the receiver. The receiver is modeled as just 2 capacitors. We're going to talk about a lot more about this later. Okay, and then we want to make sure that when the signal is transmitted from here to here, it's still a good signal. Okay. That is, it maintains its integrity. Okay. It's simple, right? But it's not simple because there are a lot of other effects. For example, the driver itself may not be ideal. It may not be able to generate a signal, very good signal. And the receiver may not be ideal. It may cause some distortions. And then on the trace, there might be reflections. Okay? And there might be some interference from other traces. Okay, so there might be noises added to the trace. And then you have a power and ground. Okay, you may have noise on the ground or noise on the power. Okay, so if you look at the picture, you can envision that there might be noises added almost everywhere. Okay, so high-speed digital design is about how to deal with these noises. Okay, all right. So what is signal integrity? High-speed design is about signal integrity. Okay, signal integrity is about interface between ideal, functional digital design like Verilog. In Verilog, you don't see noise, right? You don't see interference. And the interface between this ideal digital design and noisy analog reality. Okay, as I said, electrical energy is transmitted as field. Okay, there's no circuit in nature. Okay, so there'll be a lot of noise added to it. Okay, it's a boundary between electrical design and physical layout, like printed circuit board design. That's a physical layout. Okay, it's about to build fast digital hardware that really works. Okay, and it's about design for manufacturability, reliability, and the electromagnetic compatibility. Okay, we're not going to talk about these issues, although these issues are very important. Okay, in actual design, but in a university environment, we don't talk about these issues because they're too complex, too complicated. Okay, to talk. Okay, so but when you design an industrial project like Logitech, okay, they really need to think about manufacturability, reliability, and EMC. Okay, these are very important issues, but we don't talk about those issues. Okay, okay. And William Daly wrote a book on this topic. He called his book Digital Systems Engineering. Okay, we always talk about digital systems. Okay, when you see I'm taking a class on digital systems, that's basically logical design. Okay, so I can show you a very simple idea of where's the eraser? Right here. Okay, what we're talking about here. So, if someone asks you what is high-speed design, high-speed digital design, right? So this is digital signal. Okay, this is digital signal. You have logic 1, logic 0, logic 1. Okay, so when you write a Verilog description of circuit, you're trying to send 0 and 1 and then process 0 and 1, right? So that's logic design. Okay, so if you are concerned about this part, then you call it it's a logic or digital system design. Okay, that's what we're concerned. Okay, all right, logic design or digital system design, where we talk about this part and this part. Okay. What else do we need to worry about when we design digital systems? So we've covered this part, right? We've covered this part. What is missing? Which part is missing in this waveform? The edges, right? That's where high-speed digital design is about. High-speed digital design. Okay, it's about these edges. Okay, that's why William Daly called his book Digital System Engineering. Okay, so this is about engineering. And this is not engineering from his point of view. It's about math. Okay. And if the speed is low enough, we don't have to worry about this. Okay. At low speed design, this is good enough. Okay. Because the speed is low enough, and we don't have to worry about the rise time and fall times and so on. But if the speed is high enough, then we need to worry about the rise time and fall times. Then we need to do some engineering. Okay, so then we need to worry about noise. We need to worry about signal speed, signal transmission speed. We need to worry about timing. We also need to worry about power distribution. Okay, so when you have logic 1 and logic 0, you don't need power. Okay? The only power is needed to make transitions from logic 1 to logic 0 to logic 1 0 to logic 1. So this is where you need power. Okay? So when you see power management and so on, and then you're actually managing the power to make those transitions. Okay? So this is all these issues are not issues at all when you do logic design. Okay? That's why when you write a Verilog circuit description, you don't have any of this, right? You're not concerned about any of this. Also, in Verilog, you should be able to add circuit delay, component delay in Verilog. Okay? You can do that, but it's still very, very artificial. Okay? All right. Why is it important? Because clock rate is getting higher and higher, and then the voltage is getting lower and lower. Okay? And then you have a lot of pins. Okay? The modern chips have a few hundred pins. And then, of course, each of the pins may affect each other, may interfere with each other. So, because of these effects, okay, the issues of high-speed design or digital engineering are getting more and more important. Okay. All right. So, what's the difference between digital design and RF analog design? Because RF engineers have been concerned about high speed as well, right? Because microwave design, they're all very high speed signals, okay? And this is the difference. First difference is about bandwidth, okay? RF design usually have very small bandwidth. Most likely it's just one single sinusoidal waveform, okay? But digital designers need to worry about much higher bandwidth because we're going to talk about this clock signal, which has a very high bandwidth. Second is signal level. In digital design, we're concerned about we're transmitting voltages, volts, and in RF it's microvolts and millivolts. Okay, and then third is design density. Digital design is a very high design density. RF chips usually is has a very small few components. Okay, so and then about the design materials. In digital design, we need to make it very cheap. Digital chips are much less expensive than RF chips. Okay, because RF chips usually are small, and also you don't need a lot of them. You can afford to make them very expensive. Okay, and about shielding, okay, you can shield the RF circuit well because it's a small circuit, it's isolated, but you cannot shield digital circuit. The digital circuit is everywhere. Okay, so that's why you have to make sure your digital circuit is designed to be immune or to be able to resist noises without much shielding. Okay, and another thing is dynamic range. Okay, that's the difference. RF circuit has very high dynamic range, but the digital circuit has very low dynamic range. Okay. And the next one is about the tolerance. That is, your components values can vary. Okay, and then in digital design, the components tolerance is about 5 to 10%. That's very common. But in RF design, because RF design you can afford to spend a lot of money, so you can make it very, very. All the components can be very, very expensive and then precise and then have very high resolution. Another thing is the design cycle. Digital design cycle is very small. RF design, once you make the design, you can use it for the next 10 years. You don't have to do anything. So, okay. So that's the difference between this digital and the RF circuit.